So welcome to the Devops-Less nightmare. Today we're going to show how we managed to build a production-ready supply chain for millions of users. So I traveled South America for 4 months. I took a break from work. And when I came back to the office, my manager, Maxim, which is sitting right here, asked me, hey, do you want to get a hard task or an easy one? And I said, sure, give me the hard one. Cool, so build a system that can generate artifacts. Easy, no problem. Oh, and it has to be globally distributed, have low latency, and be resilience. Okay. And it has to serve millions of users. Oh, and also, you don't have DevOps. I was shocked. So all of us scared developers weren't sure what we're going to do. So we decided to embrace serverless. So hey, my name is Gabriel. I'm a software engineer at AppsFlyer. And before this project, me and my team had almost zero knowledge in DevOps and in AWS. And we're going to show how we managed to build a system that's going to serve millions of users without any DevOps effort. So what is AppsFlyer? We're a mobile attribution and analytics platform. We help a customer make good decisions based on analytics data. And we're talking lots and lots of data, lots of events. 50 billion clicks each day, 1.5 billion app installs each day. So lots of data to handle. And the main product, or one of the main products is our SDK. So a reminder for people who doesn't know what an SDK is. Basically, a dependency package like an NPM, if you use Node.js, for example, for mobile apps. So the developer adds the AppsFlyer SDK to his app as a dependency, and then he can send events using an API. Easy. Then you can check those events in the AppsFlyer dashboard. It's going to show events, installs, uninstalls, everything related to the app, outside and inside, and make better decision about his app. Cool. So challenge time. What is the challenge then? So the challenge is that each mobile app needs a different set of configurations, features, and security patches. So I'm sure most of you have a duck debugger sitting next to your monitors, and each one have a different duck debugger. I have a Batman one, and you communicate differently with your duck debugger. And each one has different needs from his duck debugger. So similar to a mobile app that has different needs. So think of AppsFlyer like an SDK factory. We would like to generate a unique SDK per mobile app. So we would like to provide a customized and optimized SDK for each app, exactly like these many unique duck debugger in the store. To emphasize this more, what's the difference between AppsFlyer CI to a normal CI? So a normal CI have a single Git repository with single output artifacts, meaning one SDK for all. AppsFlyer CI, on the other hand, have a single Git repository, multiply that by millions of apps, multiply that by lots of app configs, and you're going to get almost infinite numbers of SDK. And we need a unique SDK per mobile app. Pretty crazy. So after we understand the challenge, let's see the requirements. So first of all, we'd like to provide a great user experience when delivering the SDK. Hopefully, it could be seamless. Every version of the SDK should be unique and compiled per mobile app. And we would like to allow on-demand updates of the SDK. So the end goal is when the mobile app developer builds his app, add AppsFlyer as the dependency. An API call is going to be made to a repository. And as a return, he's going to get a unique SDK just for his app. So in order to achieve the goal and to overcome the challenge, we need a great architecture that's going to embrace serverless. So remember, we don't want to deal with all the infrastructure and everything related to servers and containers. We would like just to focus on the product itself. So what are the requirements for this kind of architecture? So we'd like the components to be decoupled so we can modify them, change them as we'd like. We'd like everything to be fully managed, so we don't have to deal with all the maintenance of servers and containers. Of course, it has to be easy to configure and flexible. If we want to allow more CPU, allocate more memory, should be easy. And of course, scalable and highly available, talking lots and lots of data. It has to be cost efficiency as well, as cost efficient as possible. So these are the requirements. Now I'll show you the user journey, user flow. So we start with a mobile app. The user, the developer build this app, add AppsFlyer as a dependency. An API call is going to be made to Ingress, which is going to handle the data. Then we're going to have an orchestrator. It's going to be the glue of this whole architecture. And basically, the main thing the orchestrator is going to do is start the compilation process. Here, what we're going to do is generate artifacts. Here, we're going to generate the unique SDK per mobile app. We're going to go back to the orchestrator and push the artifacts to a repository. And the developer is going to get a unique SDK for his app. So let's start with Ingress. Nothing too complicated. We have API gateway as the front door for API, SQS that can handle multiple messages at high volume reliably, and event bridge, an event-driven component that connects SQS as a producer to the rest of the architecture will be the orchestrator, which I'm going to explain in a bit. So nothing too fancy, simple Ingress. Next, I'm going to jump to the compilation component. I'm going to skip the orchestrator for a bit, but we're going to go back to it. So compilation. Basically, what we'd like to do here is generate the unique SDK per mobile app. So compile source code that's going to generate artifacts. So the question is, which AWS component should we use? Which service can help us compile the source code and generate the SDK? So we went for a compilation journey here. And I'm going to show you 3 candidates. So we had a naive start. We used Lambda in our team. We love Lambda. And we thought we can make it work. So a couple of bullets about Lambda, if you don't know. Pretty easy. You upload, and Lambda you upload your code and in a form of function, and Lambda runs your code. And you can set events that's going to trigger this Lambda. And of course, everything is handled. We don't want to deal with all the infrastructure. The reason it failed is actually limited environment and restrictive disk space. So we had to allocate more memory and give permission to folders. And in the end, it was hard to deal with the artifacts generation. So we had to ditch Lambda, even though we like Lambda. Then we found something that worked. We make it work, but it didn't fit the architecture. So code build, basically a managed CI of AWS. It compiles source code. You fetch source code from a source repository. You execute build commands using a file, and automatically everything is handled. Again, infrastructure, all the infrastructure needed. So that sounds like a great solution, but we had issue with it fitting our architecture. So it wasn't flexible. It was hard to change the OS and the source repository. And we had to ping it every couple of minutes to see the status of the compilation process. So it wasn't designed for our special unique CI pipeline. So we had to ditch code build as well. And then we found something that worked and fit, which is Fargate. In Fargate, you run containers. Basically, you deploy your containerized application using Docker. And again, you don't have to handle anything, everything, all the provisioning and scaling of the computing resources needed to run your container. Everything is handled. And it worked and fit, and the dog is happy. So again, why Fargate is great. So it's decoupled, it's event-driven, you can seamlessly integrate it with other AWS services. It's fully managed. We didn't have to handle all the provisioning, scaling, and maintenance of the container. Easy to configure and flexible, allowing more CPU, allocating more memory, really, really easy. And scalable and highly available. We're talking lots and lots of data, so we have auto-scaling and cost efficiency, pay as you go. So every time you use it, you pay. And basically, that's the compilation component. Now let's look at the glue of it all, the orchestrator. Basically, in every orchestra, the musician knows how to play, but they need some kind of conductor who's going to synchronize all the tasks and handle them. So let's see what the orchestrator is going to do. So first of all, we're going to validate and check the parameters, check they are valid, check that they exist. The main thing we're going to do is start the compilation process, called the Fargate task that I just showed a second ago, and push the SDK, the artifacts that are generated, to a repository. Then basically get a response, either we successful or not, to if we need to debug, if we have errors, and have some kind of monitoring. Cool. So the question is, which AWS component should orchestrate our tasks? And I think this is the most fun and exciting part of this whole architecture. It's the most fun tool I used. It's called a step function. Basically, a drag and drop UI. You drag and drop AWS component, you drag and drop if statement, for loops, whatever you want, and it builds this nice state machine where you can build actions, event-driven actions for your application. And the magic is that you don't need to write code. So everything is built automatically. Again, why step function is great. So it's event-driven. You can coordinate and sequence multiple AWS services. It's very, very easy to build and configure. It's fun to build and configure. It's really fun. You got error handling included. Monitoring, CloudWatch, so everything is monitored. And testing, you can redrive execution. You can see where in the state machine, in this big tree, it fails and actually debug it. And there's an API to it, so it's testable, which is great. So now, because this DevOps conference is all about Halloween, so it's time to scare you all and show you our big, scary, and intimidate step function, which looks scary, but not really. So I don't have time to go over everything. But you can see there's a start and there's an end to it. And I'll show some parts. So for example, this part right here, what do we do here? So here, basically checking, it's an if statement. You drag and drop this choice state, and you're checking if the parameters exist, checking if the parameters are valid, and you can apply conditions, and yeah, basically an if statement, and no need to write code. So then we have this line, this big line at the bottom, basically error handling. So we gather all the errors and sending an API gateway request, and then we can debug it. So for example, parameters are invalid as one of the errors. Cool. But the main thing the step function do is, again, start a compilation process. We want to start a container that's going to generate the artifacts, generate the SDK. And you can see this part right here. This is going to call the Fargate task. And the question is, why the hell do we have 3 Fargate tasks or more? Why there's multiple Fargate tasks? So again, a Fargate task will run container that will build the SDK, will generate the artifacts. So the question is, why do we have multiple of Fargate tasks? So our team actually decided to build an SDK engine. So an engine to build SDK. We're going to have multiple SDK engines. And we would like to be able to add every new engine to our architecture. Later, we can go and choose in the step function which engine to use. This is why we add multiple Fargate tasks. So basically, each Fargate task, you can see I have multiple Fargate tasks, going to use a specific SDK engine. So Fargate task number 1 is going to use SDK engine v1. And then we can choose the Fargate task in the step function. All the SDK engines are going to use as a base image. A container is going to have Android environment. Why? Because we would like to build, again, SDK for example, SDK Android apps. So we need some kind of Android environments, Android tools to build it, and some code to run it. We love Go, so we use Go code in the container. And all of this is stored in ECR. If you know what an ECR is, basically a container registry, but the repository where we store the containers, like AWS Docker Hub, basically. And the great thing about this is that, let's say the SDK team decides to release a new SDK engine tomorrow. You just need to add a box here, and because the system is decoupled, it allows modularity in the system, and it's very easy. You just add a box here, you add the Fargate task, and you can choose it in the step function. So this part right here is called ECS cluster. So on the left, the repository for our containers, and on the right, the place where our container is going to be running. And another look at this scary architecture. We have ingress, step function, ECS, and ECR. And now I'm going to give the stage for Eitav to talk more about the repository.
Thank you, Gavri. So I'm Eitav, a Senior Solution Architect at AWS. And like my friends at Amazon, I also like to deliver packages. So when Gavri mentioned that I'm going to talk about the repository, it's not actually true, because I'm going to talk about how the repository is going to store the packages and how these packages is going to be delivered to the end users. And let's deep dive about the requirements. So for the package repository part, we had few requirements. The first one was it should support standard package repository. Some kind like of Maven, NPM, or PEEP. It should support the standard protocols of the repository. Second, it should be global distributed, because AppsFlyer already have customers around the globe. Third, it should support custom authentication, because again, AppsFlyer already has existing customers that have an existing authentication method. And last, we aim to have a low latency, because all of us want to have a great user experience. Combine these requirements with the existing project requirement, as Gabriel just mentioned, led us to draw on a whiteboard, as all teams draw on a whiteboard. And we thought about a very simple solution. The solution includes an ingress that will have an authentication layer. The authentication will have some kind of custom proxy. This custom proxy is the self-developed code that AppsFlyer need to develop in order to deliver the packages. This need to mimic the protocols of Maven or NPM, etc. The custom proxy will fetch the data from the storage, and the storage will contain the lovely packages. And from AWS perspective, it looks something like that. In each region, we will have a load balancer. After the load balancer, we will have the custom authentication. The custom authentication will, if the user authenticated, it will reach out to the application that is written maybe in EC2, and the EC2 will proxy the data from S3. And it's not ends just like that, because now we need to replicate it to another region and maybe another region. And let's see how the challenges are stand with this architecture. So first, it's not a standard package repository. As I mentioned, it's a custom proxy that AppsFlyer need to build, and which is very difficult and challenging to maintain these protocols. Second, it's semi-global distributed, because it really depends on how many regions the clusters will be provisioned at. Third, the latency really depends on the custom proxy and how well it's built and maintained. And it's semi-managed, because some of the components here are not managed by AWS, and the shared responsibility is very tricky. And last, sorry, it's not last, but the aids of the configuration, it really depends on the expertise of the team at DevOps. And as Gabriel mentioned, at the time, there is zero DevOps experience in the team. And last, the cost efficiency, it's really questionable, because we're going to have multiple regions with multiple components just sitting out there, and we don't know if it will get traffic, but it's still needed there. So from a solution, it turned out to a naive solution. And I'm sure that you all can relate to, because we all been in these nice whiteboards. And with a frugal mindset, we thought to ourselves, why not to pick off-the-shelf products? Because someone else already fixed this issue for us. And when picking out off-the-shelf products, this architecture looks much more easy. We have a user that will fetch the package from a third-party package repository. Third-party package repository are out there. There's many vendors that have these capabilities. Some of them are out in the hallway. So from AWS perspective, the user will fetch the package from CodeArtifact. CodeArtifact is a managed service to store and serve your artifacts. And you probably think to yourself, okay, problem solved, right? We have a very simple architecture with managed services, but let's see how it stands with the requirements. So it's not global distributed. CodeArtifact is a single region. Second, it does not support custom authentication, meaning the current AppsFlyer customers need to change the way they authenticated with the system. And the latency is questionable regarding from where the user are coming from. And it's highly not decoupled, because now the end user of AppsFlyer need to know how to use CodeArtifact. And we can now change CodeArtifact behind the scenes if it's needed. And when we saw all these red crosses and challenges, we thought to ourselves, maybe a CDN can help us here? CDN, Content Delivery Network, is usually being used to serve images and videos. But CDN have some features that will allow us to overcome some of those challenges. So let's cover up some of the AWS Cloudfront CDN and to see how it stands out with the challenges. So first of all, AWS Cloudfront have 600 points of presence around the globe, meaning that when the users try to reach the servers, first of all, they will get to these 600 points of presence. And these 600 points of presence also contains a cache layer. So if the same content being requested again, it will be served from a nearby location to the user. Last, the traffic between the point of presence and the servers itself is not via the internet. AWS have a network backbone which is private to an AWS. It's a fiber network. So from the traffic between the point of presence is going to AWS via a much more reliable and fast way. Let's cover some of our features of AWS CloudFront. So we would like to use a compute. So for CloudFront, we have two ways to run compute. We have a Lambda at edge and CloudFront function that can be done before the cache happens. And after the cache, we can run Lambda. And we all love Lambda, right? We are in the serverless track. And we combine it with the last component, which is Amazon DynamoDB. Amazon DynamoDB is a NoSQL database that can support nearly unlimited throughput. It supports global replication of the data with the click of a button. The company does not need to understand how to replicate the data between different regions. And lastly, it's serverless, because, right, we are in a serverless track, so we must pick a serverless solution. Let's see how it all combined together. So we have a user that reaches out first to a CDN. The CDN does authentication for the user. If the user is authenticated, then the CDN is being used as a reverse proxy to the package repository. As a reverse proxy, we don't need to handle the protocols, because the protocols are being handled by the package repository. Now let's draw it in AWS icons and logos. We have a user that reaches out to CloudFront, the 600 point of presence. CloudFront runs the Lambda at edge, which check via Amazon DynamoDB if the user is authenticated or not. And if so, it's just being proxy to CodeArtifact. But it's not just like that, because now the content is being cached. Meaning, when the second user is requesting the same package again, it will no longer trigger the Lambda at edge DynamoDB or the CodeArtifact. It will be served immediately from the cache layer. And this is quite neat. And now let's see how it checked out with all the requirements. And I will go over it quickly, because it's all marked with green marks. So it's standard package repository. It's global distributed around 600 points of presence around the globe. It supports custom authentication using Lambda at edge. It has much better latency because the majority of requests will be served from a cache layer. It's highly decoupled because now the users only know CloudFront. We can change behind the scene the Lambda at edge, DynamoDB, and even CodeArtifact without the end users know about. It's fully managed. All the components here are serverless and managed. It's easy to configurable, but not a DevOps developers. And it's cost efficient because all the components here are pay as you go. Okay. And for the last package I'm going to deliver, and it's the packages we all love, it's the takeaway. So the takeaway here are quite simple. Remember the developers before that Gabriel mentioned, they are no longer scared. Serverless takes the scary away. It just gives you the ability to explore and change things in your components without the need to scary that something will happen. And if it happens, it's very easy to revert. With serverless, you focus on the thing that's important to your business, And if it needed, it can be adaptable later. And last, but certainly not least, all are welcome. No longer silos of developers or silos of DevOps. Everyone can build systems that are production ready. And to summarize with Andy Jassy own words, Andy Jassy is Amazon CEO. If Amazon had to start over again, it would be serverless. Thank you all. If you have any question, we will be in the hallway. Have a good day.